Okay, we can have a panel discussion now, and questions from the audience will be invited after the three panel members have given their opinions on the questions that we're going to pose. And I'd like to introduce, while this is happening, the three panel members, starting with Arwin Pearson from Hamburg, Director of Haber and Professor of Physics, Hamburg University, and Ashwin Shari, who is at the Max Planck Institute in Göttingen and is head of the structural mechanism and dynamics group there, biochemistry and mechanisms. And last but not least, and not smallest, Dave. Tall. So of course, I wouldn't comment on the other dimensions. Dave Brown, who is an honorary professor of structural biology in University of Kent, and also works in the pharmaceutical industry. And so I'm just going to introduce, I don't want this to feed back, so I'm going to give you the other. So can you hear me at the back? You're not going to sleep? Yeah, great, thanks. So the kickoff questions that the panel are going to perhaps give us their opinion on, or not all of them, but some of them, I'm going to give them 2 to 3 minutes each to give us their starting opinions on these questions, or the questions they'd like to answer. What unconfronted problems does the field still face? What problems are now essentially solved and we can shelve them? Where should future method development be focused? What challenges are emerging from new experimental developments? And do new experiments provide new perspectives on old problems? Okay, so I'm going to abuse my chair's privilege here because I've got the microphone at the moment and it's on. I don't know if any of you are old enough to know that we used to have a non-decimal currency in this country where there were 240 pennies in a pound because there were 12 pennies in every shilling and there were 20 shillings in a pound. And I spent my youth adding up pounds, shillings and pence. So that's where the chair's tuppence is coming from. So my comments on this very quickly is that we're a very mature field now. I gave up nuclear physics because it was a very mature field, but I haven't yet given up crystallography. Cryo-electron microscopy is now where MX was approximately 20 years ago. You could argue about that year, how far back or how far where we were then. There are new possibilities in MX through the hardware and software developments, and we've heard already about some of those in the Diamond user meeting, serial MX, time resolution, to elucidate pathways of enzymes and biological molecules. We now have little need for MIR. I think I looked in the database and I think there were only 4 MIR structures deposited in the PDB in 2023. Maybe there's another one put in on Christmas Eve, on New Year's Eve. And we probably don't even need seleno-met phasing now because we've got all these models from AlphaFold 2 for molecular replacement. We still need to upgrade our equipment, and we've heard quite a lot about that this afternoon, how various bits of equipment are being upgraded. And we still need people who understand what on earth in these computational black boxes. And I think that's a really important point from my point of view, because then they can be modified appropriately to go with new developments. And also there's a whole question about the future potential for macromolecular crystallography at XFELS, and we may not have time before tomorrow morning to get into all these questions. So I'm going to hand over to the first of our panel, and I'm going to choose Dave to go first. Is that all right?
That's fine. Okay.
Yep.
So I'm going to do the usual politician bit and not answer Elspeth's questions, but highlight the role that crystallography has played in the industrial sector. So as an industrial crystallographer, with the advent of cryo-EM and the AlphaFold and Rosetta-fold models, I'm being asked all the time, why do we still do X-ray crystallography? And the answer to that is those tools, whilst really transformational in terms of give us an understanding of a folding of a protein, which is maybe good enough to phase the protein. For what we want to understand in industry, and just saw the talk on how ligands bind so we can design better inhibitors for designing new drugs, we still need very high numbers of very accurate atomic resolution structures. And in terms of fragment screening as a way of finding a starting point, through to evolution of a fragment or a hit that you saw before into a known drug. We need large numbers of structures. The scale at which we can do that now is much higher scale. That informs all the AI type tools and the atomistic based FEP plus and other atomistic calculators of interaction energies, computational interaction energies. All those things still need further refinement with experimental data. So for me, one of the key principles is X-ray crystallography using a domain of interest or a protein of interest is still going to play a major role. What we are as structural biologists is that X-ray crystallography is a component of understanding the system, and the things like cryo-EM and computational modeling allow us to use that information in an appropriate sense to drive our drug design and understand our modes of interaction. A lot of the stuff around allosteric mechanisms, some of the disrupting protein-protein interactions. In our field, you heard before Elspeth asking, why did you do the crystal screen before the assay? If you've got an enzyme assay, you want to show it's inhibited. If you've got some protein-protein interaction, developing an assay is really very difficult. So disrupting protein-protein interactions through understanding allosteric binding modes or dimerization or domain through crystallographic and or cryo-EM structures is a key component of what we need to do going forward. So coming back to where should we be going? We are structural biologists. We should be doing integrative structural biology using data from multiple sources to inform our understanding of how a protein works and how we disrupt that protein function in a cellular environment is the ultimate aim of what we do. And we had a couple of talks earlier today where people were collecting data and doing XAFs at the same time. If you're going to couple that data, you need to have that data and the metadata associated with both the diffraction experiment and the XAFs linked. So we are in a data-driven society now, so we can produce lots of data. I don't think we're utilizing the data in the most appropriate fashion at the moment. So in terms of how we go forward, integrating those data sources and doing combined refinements is where I see things moving. And coming back to the conformational flexibility that we've also talked about today, clustering experiments, that conformational flexibility is exactly what those modeling tools can't predict. They can't predict water structures. They can't predict the conformational flexibility. They know there's an uncertainty, but they can't give you the normal modes that you may be wanting to actually stabilize or inhibit. So for me, there's still a huge amount of work to be done in this space to better utilize the data that we're now able to collect with these incredible sources, the incredible detectors we've got, and the fantastic automation that's been implemented both in terms of data reduction and refinement of automated refinement protocols. And I think we just need to make better use of that data.
So
slide on the side.
Slide on the back. Now, okay. So thanks, Dave, for saying a lot of what I wanted to say. So, if we think back to the earliest days of crystallography, one of the original criticisms when the very first crystal structures was done was, are these structures the biologically relevant ones? And I think that's still a question that plagues us in crystallography. We're doing increasing numbers of structures. They're often in solution conditions that are quite far from what we might find in a cell. And I think a legitimate criticism is sometimes, is this really the biologically relevant structure? We see that as well when we start doing structures of fragments of things, where we take the crystallizable fragments and have we cut away the very bits that are the most biologically interesting. And I think, as Dave says, that integrative biology side of things, where you're validating your crystallographic structure, and it has to be consistent with all of the rest of your biological data in order to make sense of it. I think that is one aspect where we still need to put a lot of work into, and we need to be basically our own best critics of the structures we produce. The structure might be crystallographically correct, but is it the biologically correct or the biologically relevant structure? And that takes us into thinking about dynamics and how structures change. And we actually, I think, have a very biased view of protein structure. And we see this in the successive AlphaFold. What AlphaFold predicts for you beautifully is the structure of a protein that you're likely to find in a crystalline lattice. Okay, because that's what it's trained on. And we have a training set now of over 200,000 structures in the protein data bank. But for most proteins, we've got 1 or 2 structures, right? Basically under the same set of conditions, the same crystal packing, the same lattice. We don't really have any understanding of how that structure might change if it was in a different crystal packing or in a different set of buffer conditions. And this is a real blind spot for us. And I think where we are now, we now have on the technological side, the hardware, the software, we have the ability to do massive high throughput experiments. And we should be harnessing those, not just to do thousands of the same thing, all right, but to be doing thousands of different conditions of a protein in order to be able to understand how that protein structure changes. And that's going to be probing variables like time along a reaction coordinate, like pH, like temperature, ionic strength, all of these things to build up a much bigger picture of what our proteins look like. And that then will be the training data for our next generations in the next 5, 10, 15 years of machine learning tools that will then be able to predict not just the structure we're most likely to find in a crystal lattice, but possibly much more broadly how that structure will change and move as it does its function.
Thank you, Dave. Thank you, Arvin. I could just say, yes, me too. But I think, I don't want to repeat anything. I think I take a bit of offense in saying crystallography is dead. And I think it's not really scientific that we should declare any technique as dead. Rather, it should be our scientific endeavor to use every technique to its best ability. And I think we've been pushing crystallography into niches where it's not very strong. And I think right now with all the other techniques that have matured and actually opened up venues there, I think we can go back to focusing on what crystallography does really well. One huge advantage of crystallography is it's a fully described experiment in a forward model. We can differ about to which degree it's described, but we know every step that follows up, which leads to a structure, which means we can also estimate the errors of every part of what we're doing, and we can quantify them. To my knowledge, this is the only technique that actually gives you such a latitude, and I think we should focus on that. One thing, allosteric networks, dynamics is absolutely correct. However, I would also argue what we poorly understand is we know enzymes do chemistry, which in organic chemistry require harsh conditions, they require organic solvents, and this happens magically within a scaffold in water. And we understand poorly little of how enzymes actually do this in very, very strong detail. Even more so, we don't understand it well enough so that we can actually extrapolate it into how we could make better drugs, which would exploit similar mechanisms, right? And I think that's something we should be focusing on. The technology enables this, but how we put this into context is up to us, and I think we should seek to expand on this in the next years.
Would any of the panel like to comment on what any of the rest of the panel said before I open this up to the floor? No? I'm going to ask the audience whether they thought the panel addressed any of these questions. I think they did, actually. Something about each of them. So I'll open this up. I do have the results of the survey that Nick Pierce masterminded before this meeting and has made the slides that I can show later of what the people out there thought, as it were, and some comments about that. But do we have any comments from the floor to start us off?
We do have a comment online from Miranda Lynch that Arwen's point is well taken, but dynamics is the key here. There is no single biologically relevant structure. And then she goes on to say it would be fascinating if Arwen's goal of finding many structures of a protein under different conditions in different space groups, etc., could be realized. then use the collection of structures to train an AlphaFold 2-esque DL-based prediction algorithm that can replicate dynamics, and then compare the structure-trained dynamic engine to the results of MD simulations based on physics principles.
Ben Max.
Would you like to say anything about nucleic acids and their role in structure and the dynamics of structure?
I'd love to, Ben, thank you. Yeah, they're a bit of a blind spot, aren't they? Hands up, I've only ever done one structure that had some RNA in it, and it was very tightly bound and stable and not very exciting. And I do think this is something we don't look at enough. It's sort of the poor sister of structural biology. Dave clearly has an opinion.
So yeah, I do have an opinion because I think so I did my PhD in nucleic acid structure, funny enough, and at the time it was small molecules binding to DNA. I think the protein nucleic acid interaction, clearly Ben, an area you know very well, is a really growing area for drug discovery, and particularly in certain cancer targets at the moment. And I think targeting RNA itself is a growing field, either with small molecules or using antisense oligonucleotides has reoccurred 30 years after it was initiated as a therapeutic modality. And I think the RNA structure, funny enough, we've just talked about the new CCP4 grant at Working Group 1, and RNA plays a major part in terms of being able to model and predict those structures. Inherently, if you're looking at those isolated RNAs as targets, they're much more jelly-like, shall we say. They're less structurally formed, rigid than proteins, but in terms of protein, RNA, protein, DNA structures, capturing these different states as drug targets opens up a much wider allosteric range of potential binding modes. And I think we've got Dave Stewart in the audience, going back to HIV reverse transcriptase and allosteric modulators that affect the mechanism of interaction with nucleic acids. You know, it's old ground being revisited, but I think it's not well described, and certainly in terms of the database of structures, it's much less populated. I don't know if that's what you were looking for, or there's a specific question you've got on top of that.
And there's a whole section of my lab in biochemistry in Oxford who would say, what about the glycans? And that they have a huge role to play, and we tend to not worry about them too much.
Yeah, and if I can come back to you on that, I think one of the myths of doing crystallography in the old days is you had to get rid of your glycans to get anything to crystallize. And I think with the advent of cryo-EM, people are using more mammalian protein production systems, and they're trying, if you're in industry, you'll go, I'm going to get this structure, I'll do cryo-EM and X-ray, and guess what? A lot of those glycosylated proteins are crystallizing quite nicely now. So I think a lot of myths have been debunked based on protein production methods.
So I'd just like to ask a question about how, because like I understand.
Could you say who you are?
Oh, yes, of course. Jesse, I'm from University of Reading, undergrad student STEM subject. I'd like to sort of understand a little bit better, like the challenges that you're encountering, sort of like bridging the gap between the technology and the science, because I understand like it's quite a big issue to, I should think, to try and like communicate with like software developers, for instance, because I come from like a software engineering background. And I understand it's quite difficult to probably communicate some of the scientific challenges and what you want to get out of the technology to software developers. And I was just wondering what is one of the bigger challenges with communication that you need to sort of overcome to sort of like improve like your methods and stuff like that, and with integrating with technology.
Yeah, I can try. Certainly, we need to communicate, and it's not a single-minded effort. It's a collaborative effort here, and I do think that we often do not speak the same language, which makes it very much different. We mean the same things often, but we express it differently. I think that's where industry has a huge leg up on us, because they're forced to actually communicate much more within the departments. As academics, it is tough, and I think that's definitely something we should try to make better.
I think interdisciplinary research can help a lot with that. I remember my first day in molecular biophysics. I worked with David Stewart there, and I had a big argument with one of the graduate students who came up from the microscope room and said he'd just seen a nucleus. And I'm like, hey, I've spent the last 11 years looking at nuclei and I never saw one. And we had quite an argument. He was quite an aggressive young man. And it turned out I was talking about the nucleus of an atom and he was talking about the nucleus of a cell. And it's a very trivial example, but it just shows how the language can be really important cross-disciplinary wise. And if we can combine data from different sources, then it's vital that we can communicate that. Do we have other comments from or questions from the audience?
Hello, my name is Emily Cross. I'm from Diamond. I have a question. What's your advice for maybe new graduates in crystallography who I guess are kind of the future of crystallography? Is it enough to be solely a crystallographer now, or should you be also able to do cryo-EM and all these other techniques?
Thank you for that fantastic question.
I mean, I think it's always helpful to understand different techniques because I think this actually makes communication better because you're able to communicate to other people better. I think as a crystallographer, because many of the things have become mature, lots of the problems actually become sample problems. And so being an excellent biochemist is probably the best thing you can do to become an excellent crystallographer or cryo-EM or whatever thing. So maybe that helps you.
So a slightly different, I agree with Ashwin. I think it depends what you want to be, right? Are you driven by the biology, in which point absolutely become a really good protein biochemist first, and then use whichever structural or biophysical techniques will get you to your answer. But I think as a field, all right, we also need to have people who are interested in becoming the crystallographic experts of the future, right? Who are going to write the next generations of software, who are going to build the next generations of really cool beamlines to do crystallographic experiments that today we can just sort of dream of. And you can make a career doing that. All right, you don't have to chase the biology. It's maybe not as easy. There's not as many opportunities, but there are opportunities. And I think as a field, we also need to be encouraging those of you who are interested in doing the methods to stick with it. And we need to be supporting you.
Yeah, I totally agree with both those comments. I think Arwen's point about you can be an expert in one thing. And in terms of industrially, we have this scientific career ladder in most companies where you stay an expert and you can actually just progress as being an expert in just one thing. But actually quite often you're learning as you keep that expertise development going, you're learning other expertises at the same time. So you grow your breadth of knowledge to see how you can utilize and impact across a wider area with your core expertise. And I think, it comes back to your passion. What do you really want to do at the end of the day? And follow what you love most.
Hello, Daniel from Cardiff University, PhD student. Just wonder, throughout the history of crystallography, one information that has been disadvantage of these is the dynamic of the protein, right? And then throughout the course of the development of the technique, whereas time resolved crystallography would try to address the problem in dynamic of the protein, especially in enzyme reaction, for example. As you mentioned that we do crystallize these things in the, I would say, artificial environment that's irrelevant to the biological context. Would there be anything that, or any issue or any concern that has to be addressed to people who try to utilize these informations?
So I'll tell you that first, because you used the word irrelevant, and it's definitely not irrelevant. It's very relevant in terms of, we do structure-based drug design, and it's the crystal structures that drive and inform the computational modeling of how to improve your binding interaction energies. So I think that's really important to remember. And from the crystallographic system, it's probably more to Aaron Nashwin in terms of these enzymes are still active in a crystal lattice. So, and they're in a highly biologically relevant solvent. So proteins, we talked about what proteins do and what chemistry they do. They do that by creating the right environment, by folding around a substrate and performing an action, and creating the right environment for that enzymology, for that reaction to happen. So they're certainly not irrelevant. And I think one of the things you mentioned there about the dynamics, and we keep coming back to dynamics, we structural biologists don't think just crystallography, think about there's NMR, which is good at resolving dynamic states. There's MD simulations that can be, that are informed by constraints that come from structural information that help us understand how the dynamics of these proteins and how they work. So we use all these techniques at the same time to better inform our understanding of whether that crystal structure, the single structure that we try and look at, is representative of a minimal state of something that we want to target or not, or is not representative and doesn't translate to what we're seeing in terms of activity from an enzyme activity assay or a cell-based activity assay. So we're always cross-correlating with other data to say, does this crystal structure inform? And at some point, it may deviate. And quite often it does at a later stage of drug development because of properties that we don't understand yet.
I fully agree, and I think irrelevant, I think Dave has addressed that perfectly. The next aspect would be, is it unphysiological or is it physiologically relevant? And I think the point Arvin tries to make is that you may happen to have a crystal structure where crystals grow at a pH of 4.5, which might not be physiological pH. But that being said, I don't think that we fully understand physiological pH. At the same time, one very important aspect which is neglected with crystals is proteins within a cell oftentimes are in concentrations which they are actually within crystals. So probably performing an enzymatic reaction within a crystal is more physiological than actually performing the enzymatic assay, because you have to dilute your proteins massively to actually follow the reaction in an enzymatic assay. So these are trade-offs, and I think what we should open our eyes to is not questioning whether it's irrelevant, whether it's unphysiological, but I think we have to open our eyes to actually employing and studying the structures in different chemical, biochemical states, which complete the picture, and at the same time look back and question whether we are over-interpreting certain aspects, which might result from crystal lattice restraints, which might result from pHs in which the crystals grow, which might result from the way we actually do our structures. But this is universally applicable, irrespective of the technique you use, right?
Yeah, and if I can just follow up on that, you should understand each method you use, and you should understand what it can do and what it can't do, right? And where the limits are of what you can interpret from that data. I mean, that's your job as a scientist, right? And we have this plethora of techniques, and you should be choosing the right experiment for your science question. You shouldn't just be saying everything is a crystallographic experiment, because that's what I do. There are times when crystallography is not the right experiment. And so you need to think about what you actually want to know and do the experiment that will get you to that answer.
And just to elaborate on that, and something coming back to what Elspeth said earlier, we're in it's interdisciplinary science, particularly in drug discovery. We had the question about communication. How do you communicate with each other? It's actually being able to interpret your results and communicate them in a relevant way, putting limits on your confidence in the data you're showing to a collaborator who is going to then use his expertise to take those results and do something with them. So in our case, that's working between a structural biologist, a crystallographer, or an NMR person, they're doing fragment-based screening, going to a chemist, through working with a modeler. We normally work with a chemist, a modeler, and a structural biologist all working together to interpret and understand the data. And it does get down to, sadly, it's not an exact science. There's a lot of hand waving still goes on.
We have a question online. What is the future of disordered protein? How are we going to address this topic?
Well, I think NMR is a very good place to start. And not only NMR, it's actually, that's where interdisciplinarity plays a role. There are some interesting results coming now out of cryo-electron tomography, where certain of these aggregates are being studied. Spectroscopic methods are very vital in this regard, but it can also be fluorescent microscopy methods, FRET, FLIM methods, and so on and so forth. I think their multidisciplinarity plays a huge role.
Yeah, exactly that. And I think in terms of looking at when that disorder changes state as well is obviously a key point in terms of phosphorylation of certain targets. There's and recognition of those disordered states by an ordered state. These are real potential drug targets.
I have a question if there's no one else.
Paul Tiley, University of Reading. As a PhD student trying to make some novel small compounds, doing some modeling and trying to get them to interact with DNA. Could I just ask you to elaborate a bit more on what the issues with physiological pH, and maybe I'm working at the wrong pH trying to get solubility and binding. Thank you.
It's not also solubility of binding, of course, because this is going to influence your compound as well as the protein and whatnot. But I think it also affects each and every target site of a small molecule binder, right? So if you're at pH 4.5, you want the protein to bind to a carboxylic acid as a carboxylate. You're probably not doing a very good job because the carboxylic acid is going to be protonated. And this can exclude binding, which might not do the job, but perhaps you can add something there.
I'll meet you in the bar afterwards.
I've got a question online from Paula Salgado. So crystals or cryo-EM structures are experimental models. AlphaFold2 are predictive models. How do we train the non-structural biologists to interpret all these models cautiously and wisely to understand their biological problem? With AlphaFold2 and all the buzz around the protein structure problem being solved, this is more important and relevant.
So thanks, Paula. It's a nice point. I think it's part of a much bigger problem, which is how do we deliver structures to our end users in a way that reflects properly our confidence in every part of that structure? And I think this has been a challenge for crystallography right from the beginning, and also for cryo-EM and NMR. So how do we, when we look at crystal structure, we understand what we mean by high B factors. We understand when there's multiple conformations or something not modeled. We understand the decision process that's gone into that. But a downstream user maybe doesn't. And I had first-hand experience of this. I did a course with Sarah Harris for molecular dynamics people, and I got to introduce the protein data bank file, right? And so I had one for them to look at, and I went through the header and they were gobsmacked. They said, we just delete all that and we don't read it. And I was like, but there's lots of useful information in there about the structure. And working out how to reflect that data back to the users is, I think, a real, coming back to communication, it's a real communication challenge. And we're not good, I think, at indicating clearly and unambiguously where we're confident and not confident in a structure.
So I'll just add one more thing to this, which is I think we also have to use precise language, right? So one part of it is near atomic resolution structure. So what does this exactly signify? In many cases nowadays, this can signify 4 angstrom resolution. It can signify 5 angstrom resolution. I think what it was originally intended to signify is it's just outside of the range where single individual atoms were actually resolved. So it was just outside of 1 angstrom resolution. But we stretched this. And since we are not using the language correctly, we cannot expect other people to use the language correctly. And I think that's an impetus on ourselves.
I guess I have a related question actually on like data quality metrics. At what point can we stop using R merge in table 1? Like, is that no longer relevant? Because like we all know the problems with it, and we generally go to RPIM, but reviewer 2 will always request R merge.
You're giving the panel to make this decision. Again, this comes down to education, and it comes down to the fact that, you know, when I trained as a crystallographer, you could spend your PhD learning all the niceties of crystallography and come out with one structure, or maybe not even a structure, and still graduate and feel you've done a good job. And nowadays, we expect students to come out with tens, hundreds of structures and a whole load of biology as well, because the individual experiments have become, easier is maybe the wrong word, but they've become more routine. And this means that we're not training in the same depth. I'm not really sure where I'm going with this point, but it is a training question, and it's how we convey this. Mike maybe got a comment, but I don't know if one of you two want to.
No, I think it just comes back to that question you said before about communication of the quality of what you've produced. And I think that's where we're very fortunate as a community that we have deposition standards that are upheld in terms of what has to go into a deposition. And then it's actually, you know, it's up to the RCSB and the EBI and the PDB Japan to say how they're going to publish that information to less educated users. And they do a pretty good job in saying whether this is they cannot police it. They can only say that this is the data we've presented and we present this back in an appropriate way, but they present it in a way that is this above or below normal, what you'd expect from a structure of this quality. And I think people are, you know, relatively capable of doing that. The unfortunate part is when people show a structure in 3 dimensions or a 2D image of a structure, they don't say whether it's a crystal structure anymore or a model. And at the end of the day, the crystal structure is a model of the X-ray data. So we produce models as well. And I think that definition of an experimentally derived model versus a computational, and if you talk to a computational chemist, they will say that they are experimentalists. So again, coming back to your terminology, having common terminology that everybody understands what the likely quality and likely errors are in what they're looking at is the most important thing.
Yeah, the ratio of number of downloads from the PDB against qualified, in inverted commas, crystallographers is alarmingly high, in that probably for every 10, every one crystallographer, there's at least 10 or 20 people who don't know what any of these parameters mean, who are using the structures. Mike Huff.
So we've talked about the role of molecular dynamics and structure prediction as bringing computation into crystallography. I'm wondering what you think about a role for DFT and QMMM type simulations in understanding enzyme mechanisms and ligand binding.
Yeah, I think it's underused in my personal opinion, and there should be much more. I think one of the reasons it's underused is that we cannot all fully agree and make sense of how to use it well, but I do think this needs to increase. In high resolution structures, there's no way out of it, and that's often the only way to validate some findings you have.
Yeah, I agree. It comes back to the integrated approach, and you know, QMMM is something we do, but it's the scale at which you can do it for some of the interactions we want is still somewhat limited. The computational power is getting there, but it's not, even with quantum computing, it's still only tens of atoms, not hundreds, from what I understand anyway.
up the back there. Yeah.
Hello, my name is Utsila from the University of Bath. So basically, I wanted to ask what role, if any, large language learning models such as ChatGPT may play in crystallography. I myself am a biochemist / crystallographer, and I'm not sure if there's any role these new tools might play in the field, because I only noticed using them to like try to summarize structural papers using this technology, but it fails miserably. So I wanted to see if you envision any role for these technologies. Yeah.
Yeah, I can start. So I think there's big potential, and again, coming back to the communication thing about using a large language model that could possibly make it easier for a non-expert user to ask questions like assess the quality of the model, or which bits of the model can I rely on, and having that back-ended with something that captures the expertise of a crystallographer. In the same way, when you're faced with maybe hundreds of data sets from your drug screen, which one is most exciting for me to look at would be your natural question. And at the moment, you trawl through tons of metrics, but I think there again is mileage there for that kind of model to do that for you. How to do that and whether we've got enough training data for something to do that reasonably, I'm not sure yet, but maybe in not too long, as the real sort of high throughput beamlines really come into their own. And I think there's the stuff that I've seen that Diamond are doing, and that Patrick mentioned now as well, Daisy and a DSRF, with the throughputs that are starting to become possible. I think we're going to have some kind of interface like that to the data, particularly for people who aren't deep experts and are coming in.
I think we have another question on Slack. Oh, Graham.
It's a question back about this, actually. Where was the point where people stopped being scientists? In the sense that the PDB contains many measurements, or contains many models derived from measurements. These have their own intrinsic benefits. Some of them are very good, some of them are less good, and so forth, right? But surely we are scientists, and part of your job is to actually sift through the data that are presented to you and make your own judgment calls on what is good, what is not good. I mean, okay, I'm grumpy old man and I hate it when people go, oh, but I used ChatGPT for this. Yes, it made up lies, right? But at which point did we say, no, it is now the job of the creator of the data to digest it in a way that anybody can interpret it without making mistakes?
I think, Graham, at the point where we all started to want our models to be used by people who weren't crystallographers, right? Because it's exactly that question. It's, how do I sift into this data and work out whether the model that's proposed is reasonable or not? I mean, in principle, to do that properly, you need to be a crystallographer, right? Or at least have had extensive training in what's going on there. And a lot of our users simply aren't.
Also ask you a question back, which is, how many times have you gone into a specific structure, redone it with better tools, and looked if everything is as valid as the original interpretation?
Okay, I have never done that, right? Because that is not the job of work that I do go back and reprocess old data sets. And it is certainly the case that when you reprocess old data sets with new methods, you get a bit more out of it. And that just says that actually, if we have the data available, we can iterate on that. But it's part of what we should be doing is actually iterating on the data rather than just saying this is a gospel structure. It is.
Thank you for that interesting comment. Rob, you get the last question from the floor. Down here.
Sam.
Robert Öffner from Aztec Therapeutics. My impression was that during the pandemic, scientists were being hailed as heroes, and the public really appreciated that. Do you got any suggestions on how we can ride that wave and still not fall into disrespect as being evil, nerdy scientists that nobody understands in the coming future?
So I think CSP4 study weekend is a good start. And I remember a study weekend over 10 years ago now, and talking to Richard Palpty, and he said, we're united by a common method, right? That all of us love crystallography. We work on radically different things. And I think crystallography as a field is a really good example of people with many different scientific interests coming together and exchanging about their method. And I think we should be being a role model for everybody else to work in a similar way.
I think I would like to emphasize communication out there again, because I have to say I'm probably very bad at it. So we should speak to the public, and we should speak to them in a language which is probably more accessible. And one of the reasons is that scientists were hailed as superstars during the pandemic was all the science was very tangible, because it was a problem everyone was faced with, and it was a tangible approach to remediate this problem. And oftentimes the science we do is not as tangible, and partially because we don't communicate it as well, and partially because it doesn't have an immediate goal as well.
Yeah, and I think on that note, I mean, it was in everybody's mind what the scientific problem we were tackling. I think there was a huge amount of collaboration and pre-competitive collaboration in terms of understanding what was going on, which again, I think as a community, we are a community linked by a technology, but actually it's a technology you only have to be a small group to execute. Whereas if you go back to the physics community, the only way they can get enough money to do an experiment is by getting together and lobbying governments to build a huge particle accelerator, or the astronomy industry to put some big thing into space. We don't have to do that. Unfortunately, we can do things quite cheaply and readily. And actually, you know, one of the things that for the first time in terms of what we were doing as a structural community and understanding at a structural level how this virus was working was by sharing that as a collegiate approach. It was probably one of the first occasions we've done that. AIDS probably was the other epidemic that where it was done, but not in no way to the same degree as it was done during COVID. So a common cause and pre-competitive collaboration, I think, were the main drivers to and informing an uneducated community about what we can do to tackle those problems.
Thank you very much, everybody, for these comments, questions, and especially our panel. I'm just going to show you the results of the survey now before we go and have our lunch. No, it's not lunch, sorry. It says our dinner, and look at the posters and talk to each other about PHs in the bar. The survey results, and this is the people who answered the survey. I was quite interested in this because it seems to indicate that the PIs have a lot more time on their hands than the graduate students, because we had 29 PIs answering and only 4 postdocs and 4 PhDs. Is the field of crystallography dead? Well, the vote was yes was 0, no 47, and maybe 6. So there may be people probably have had an interesting listening to this about what it can still do for us. As we've heard, it's still very useful in drug discovery pipelines, and the time-resolved and serial crystallography is still in its infancy. We need experiments because evidence from experiments is essential to train better models, to predict better things, to go and test them experimentally. So it's a sort of cycle, really. We need a high level of positional accuracy, as has been said, for ligands, especially by David. And this is only accessible at the moment with crystallography. So it might die or at least slow down a bit. But if structure-based drug design can routinely be achieved by cryo-EM. These are not my ideas, sorry, these are all comments taken from the survey. So that they've been taken off the huge spreadsheet, which Nick got. So when pharma companies shift their resources to in-house cryo-EM, maybe they won't need so much synchrotron beamlines, but from what David said, that's not so. So one of the questions was what hasn't got easier? Crystallization is obviously being crossed out because everybody would have written that. Data collection and validation have got easier, but crystallization is sometimes extremely challenging still. Deep learning could be helpful for targeted and local structure determination needs, assist in resolving ambiguities, simulating different configurations that could guide refinement. So we should be focusing on poorly resolved but functionally important regions of protein structure, and that came up in the discussion as well. So model building is a bit like, well, it's still an art in a way. Computers should be able to place atoms in electron density better than humans, and this person obviously thought they couldn't do that yet. What are the obstacles in applying new experimental techniques? Dynamics, as we've heard tonight as well, is still a problem. Well, a problem to be tackled, I should say. CCP4 and Phoenix are great, but one designed to help crystallographers in 1990 or 2010. But now we're at 2024. So this person clearly don't think we don't have enough GUIs or something. I don't know. That the software has got left behind. I'm not sure that we agree with that. Do we, panel? No. Okay. So while these techniques are evolving fast, there's still a lack of easy to use experimental analysis tools for the broader adoption. It appears only a small set of expert groups are able to perform these experiments, which needs to change. So I presume that that's sort of time resolved and free electron laser experiments mainly. Finalizing the models, again, interpreting the results, placing them in context. No AI geek wants to touch that with a barge pole. Is that true? Forgot any AI geeks in the audience who would like to tackle that? Yeah. Yeah. No. And then this is the final one. Any questions or discussion points? You can, or how to hype up crystallography to the youth. How do we persuade people to be crystallographers now? The resurgence of room temperature crystallography gives us more functionally relevant than low temperature structures possibly. However, cryo-EM is always conducted exclusively at the moment, or it's cryo at low temperature. Is this a problem? Why is this never discussed, not discussed? That the cryo-EM structures are all at 77 Kelvin. The biggest threat to crystallography, this is a comment, and cryo-EM in academia are non-structural biologist grant reviewers. This has been a subject on the CCP4 bulletin board, with people asking how to persuade grant reviewers and grant givers that we still need to do crystallography. And I think it is a real problem to communicate that adequately. They believe that AI has already solved all the structures. And I've even suffered this in my own small social circle in Oxford, where my best mate is she's got a PhD in German literature. And she emailed me after listening to the Royal Institution lectures, which I had encouraged her to do, to say, does that mean that you can finally retire, Elspeth, because they've because they've solved the problem? So, I mean, what I'm trying to say is that this perception is very, very widely held that this problem is solved. Should we include QM boxes in automated refinement of ligands? That's a good question. Yeah. Yeah. Okay, so if humans can judge data quality, and Nick has assembled this for you to enjoy, but I would like to draw the session to a close. Thank the panelists very, very much for putting themselves on the spot here, and to thank you for coming and listening.